everyone. I am Nikolai Hendrickson. I am a senior head of sales for the Bridgel. I've been working at Bridgel approximately 5 years. So we are happy to do this webinar in collaboration with MES, one of our definitely our largest partner in the US. And we are a company who is been working approximately 50 countries and worldwide. So let me introduce to you guys what will be in the agenda. We'll cover a little bit, just introduce Bridgel. We'll discuss the challenges from EV fires, and there will be a focus on that towards containment. Then we'll go and cover background on recent concerns, containment versus suppression, to compare. And then we'll do best practices at the end, and then at the end we'll have some Q&A. So yes, thank you very much for your time. So let's jump into the introduction of the company. So prior to that, I also want to make sure. So I really hope that everyone in this webinar will be able to, some of the essential learning points would be to understand how fire blankets are used correctly, understand the difference between suppression and containment, and also why oxygen should not be introduced upon blanket, only should be introduced upon blanket removal. So a little bit about Bridgel. We are a company that's fairly new. We founded in 2014. Our technology was inspired by the NASA inflatable shield that allow us to develop two core fabrics, pyroxene and graphite. We are in 50 countries and growing. So just to illustrate you a little bit, what does the technology and what is a fire blanket made of? What is the construction? Right in front of you, you can see it's a 3-layer solution. I'm guessing a lot of you guys have already a fire blanket with you. So you'll see at the top and at the bottom, there's a coating. That coating is developed for you to combat the smoke and all that toxic vapor cloud that's coming from an EV fire. And the core fabric right in the middle is there to combat the flames, torching conditions. And those that can vary. That core fabric can either be pyroxene or graphite. So this technology is being tested and certified so we have a lot of different certifications. I think the one that has the highest correlation with EV containment, it's going to be the DIN spec, which is a new standard or certification under standards focused on EV containment. As this is a new method to deal with EV fires, it took a couple of years to have a certification that will focus solely on containment for EV fires. So that's what our blankets are certified today. Now, jumping into the challenge of EV fires, in this presentation, I want to go through thermal runaway, and I want to have a different focus. I'm guessing, and I hope everyone attending already is familiar with the thermal runaway, but maybe some of you guys don't see it this way, and I'm trying to have a different perspective on a thermal event. So in this slide right in front of you, what I'm doing is that I'm dividing 4 events and clustering into groups. So you're going to have a trigger event. You're going to have an internal chemical breakdown. So a trigger event could be, for instance, a short circuit, right? So once that short circuit happens, then you're going to have a chemical breakdown. That jumps later on into an off-gassing and ignition of that battery cell. So as you can see, a trigger event and internal chemical breakdown may last minutes or years. And in a battery pack consisting of thousands of batteries, this process may take a long time. And they will all start their unique ignition time in a different time, potentially. And then you have the off-gas and ignition, which takes much shorter amount of time. So one of the biggest risks and problems that we see when dealing with lithium-ion battery fires is that you have, for an EV, approximately 77,000 battery cells. And we could create a theoretical hypothetical example where we say, okay, we have 7,000 battery cells, and if we say that 10 of them will start to burn due to a thermal event and damage, and or let's say one starts to burn, then reignites nine other batteries, so we have a total of 10, and those burn for 30 minutes. Once that stops, it doesn't mean that you have no longer fire. What we see is that when a battery gets damaged, there's going to be several reignitions and thermal events happening with different battery cells to start to burn. So this is what we see when firefighters, for instance, are trying to put out a fire, an EV fire, that use copious amounts of water because they may be able to suppress the initial fire or thermal runaway, but then another one comes after 30 minutes, and then another one after 30 minutes. 30 minutes are there just to illustrate an example. It's not that's going to happen every 30 minutes, but it can happen after 30 minutes, after 40 minutes, an hour, 2 hours. And on worst scenarios, we see that this can happen after 2 years. We've actually tested EVs in our facilities that I ended up reigniting at the recycling facilities after 2 years. So once the batteries get damaged, reignition risks becomes a big problem. You just do not know when that is going to happen. And the other problem that we find ourselves in is that, well, the design of this battery cells, and it's already also has, each battery pack is going to have different layers of metal in them. So reaching that main source of the fire and really trying to be able to effectively cooling down the battery, it becomes difficult. And that's just the battery pack. Once you have that, you're going to have several layers that will then hit that battery pack. Usually in an electric vehicle, we have an average 9 layers. Every vehicle is obviously built in a different way, but we can expect to meet steel and an aluminum structure surrounding the battery pack. And that creates a substantial barrier that will delay or prevent water from cooling and reaching that battery, right? So accessing that main source of the fire, it's difficult. So some of the main problems that we've discussed already, it's stranded energy, which is the reignition problem. But you also have another problem, which is toxic gases. And this is what I'm going to be covering moving forward. And obviously, you also have the spread of fire that is highly correlated with the reignition. So regarding the vapor cloud, or the toxic gases generated by an EV fire, there's going to be 4 different types of absorption routes. You find inhalation, which is the worst and most damaging exposure. You can have skin contact, eye contact, and ingestion. And when you are exposed to high or concentrated high doses of this, this can have fatal or even very severe health effects. So making these types of fires very dangerous. So right in front of you, you have some of those toxics that you can find on an EV fire. We're talking about carbon monoxide, carbon dioxide, hydrogen fluoride, acidic vapors, and more. So this makes these types of fires very dangerous, and this is the type of cocktails that, as a firefighter, you will be getting exposed to. So it's very important that firefighters take these types of fires seriously. We see that there's been incidents where last year there was actually an incident where 5 firefighters were standing approximately 500 feet from an EV fire. The problem was that as the fire took so long to be put out, they were standing for several minutes there inhaling these gases. 4 of them got very sick. 3 of them who had an ongoing respiratory problems and were not able to work, and 1 of them had severe fatigue and lung damage. So that was the worst case. And this is standing approximately 300 feet from 200 to 300 feet from an EV fire. So the concentration was not as big, but it is definitely damaging. And we see that wind, it's transporting this toxic heavy metals, creating toxic residue. So that's another problem. One of the problems that we find is that, I'll show very soon a video to illustrate this with a real case scenario, is that when an EV burns, they're generating heavy metals that don't evaporate. So potentially they can stay on the surface for many weeks, months, since they don't evaporate. And very small concentrations of this can become basically dust that with wind or movement can then become airborne. And this can obviously become a post-contamination risk. So we're no longer talking about EVs being dangerous once they burn, but we're also talking about EV fires becoming dangerous in the long term and having those
Hey,
post-contamination risks.
excuse me, real quick, Nicolay. Someone mentioned that they having a hard time hearing. Can everyone hear Nicolay okay? Thumbs up.
Got a thumbs up.
Okay.
Can
Continue.
anyone else give a thumbs up just to confirm that you can hear me? Right. Someone may be having connection problems. But we've gotten already 2 thumbs up in a several 4. And yeah. So thank you for that confirmation. I will then continue. So we find that there is a post-contamination risk. So let me illustrate this with an actual real scenario. Last year, a battery plant burned of lithium-ion batteries. So 10 months after the fire, they did testing. They went around and tested the soil, and they found 55,000 pounds of heavy metals. They found copper, nickel, manganese, and cobalt in the soil samples. So this is what I'm talking about, the post-contamination risk. So this was 10 months after, where you will find this, heavy metals that don't evaporate. They were standing in the soil. And this has obviously had a huge impact for nature. But when we're talking about not a battery plant burning, but an EV, right? You're obviously not going to have 55,000 pounds of heavy metals, but you're going to have a good amount spread on that area. So here we can already use public EV composition data. So that's available for everyone. And for that allows us to understand that approximately you can have an EV battery may contain approximately roughly 100 to 150 pounds of heavy metals in them. And then we can also expect a good amount of those to spread on the environment, right? So with this real now evidence, we're now able to understand these post-contamination risks. And just to illustrate a little bit, for every small airborne concentration, for example, if you have just 0.015 milligrams per cubic meter of nickel, this may already be a risk for your health. So it takes very little. And this is just nickel. If you have a combination with nickel and cobalt and manganese and others, people may get exposed to this, small particles that become airborne in the future. So this is another topic that not everyone is discussing today, but it really brings and highlights the importance of containment, which was obviously the reason why I brought this up. Before I go more into containment, I would now want to discuss a next subject, which is recent experimental testing. So there's been some experimental testing done, especially last year, and there was some misunderstanding. So for us, it's important that we understand and communicate what was done. When you do experimental testing, you can already kind of predict that the protocols are not going to be followed. This is why it's experimental. Right in front of you, you have fire blankets. This happens to be our fire blanket, actually. And then in two tests, in one test, they were actually created a mechanism to lift the blanket several times. So this was automatically done, lifting the blanket several times. In other tests, they were trying to use in conjunction different tools and placing them underneath the vehicle. In order to do so, they ended up also lifting the blanket. The structure of the vehicle collapsed and it was found at ground level. So it made very difficult to use in conjunction any tool with the blanket. At the end, what we have found, and it was found that, introduction of oxygen needs to be carefully done. So let's now talk about knowledge that I'm sure everyone already has. So I like to use the backdraft theory because this is something that firefighters already know and master to explain the deflagration. So explosions are never experienced with an EV fire when you contain it, but the deflagrations can be experienced. And these have basically the same recipe that you have for a backdraft incident. So when you have high concentrations of fuel inside an environment and low concentrations of oxygen, and then you introduce oxygen levels and where you also have flames or heat, this can create a backdraft, right? So the same applies to a deflagration. So when you have, and I will explain this very soon. I just wanted to illustrate this, and this is just basically the reason why you can create a deflagration is because you introduce oxygen to and where there's an environment that is oxygen deprived, and then you introduce oxygen to a fuel-rich environment. So now let me show you how would a proper deployment look like of a blanket. What you're about to see is a firefighters deploying a blanket and not lifting it. So you'll see a rapid containment. You're going to see a drop at approximately 70% of the heat of the temperatures around the vehicle is decreased. You'll also approximately see a isolation of smoke and toxic gases by also approximately 70% within a minute. So those are the pro sides of containment. We're having a drastic decrease of the temperatures and of all those toxic gases. Here we can go back and start reading that graph right in front of you. So you have the blue line and the orange line, the blue one, showing the interior temperatures, and the orange one, the thermal imaging, the exterior temperatures. And you can see there's going to be spikes through the graph. Every spike is illustrating a new thermal event. So when 10 batteries, let's say, right, started to burn, they all fully burned and they went through the entire thermal runaway cycle. But then those then most likely damage other batteries. And remember that first stage that I mentioned before, that it can take minutes or years. Then in this case, after a couple minutes, this is from 27, and then now after approximately 30 minutes, another thermal event initiated, and another one after 1 hour and 45, and another one after 2 hours and 15 minutes, and another one after 4 hours and 20 minutes. So this is what I'm talking about. This is what makes it very difficult when you're trying to suppress a vehicle that is reigniting every 30 minutes and an hour, and after 2 hours, it makes it very difficult and resource intensive. And now the other side, you also have all all those heavy metals being spread through the smoke and that toxic vapor cloud. So, so this is why many firefighters choose to go for containment rather than suppression, because understanding or determining how long an EV is going to burn, and it is basically impossible at this point. And we just do not know if the vehicle is going to reignite, or when the vehicle is going to reignite, or if it's not going to reignite. So here you see the deployment of the blanket being done without lifting. Obviously, and let me tell you a little bit more about what happens when you deploy a blanket. So let's jump into best practices. So what happens when you deploy a blanket? You have immediate control of the fire. So the fire is not going to continue to spread. You're going to have oxidation of those toxic gases, which are containing all these heavy metals, as I mentioned, that can spread hundreds of feet around the area. Even actually, we've seen actually data showing that they can spread miles away because of wind. And then you are reducing environmental impact, which is obviously positive, but you're also protecting civilians around an area. And if you find yourself in a highly populated area in a city, well, containment can be very positive for everyone walking in that area and moving forward. You're also reducing the stranded energy risks. Why? Because as there is, and you should always expect or assume there's still energy in that vehicle, then you don't know when or if it's going to reignite. And if it reignites with a containment blanket on top, it's not going to be, harmful. It's just going to be isolated, or as harmful as it would be when, if without the blanket, it's just going to allow the content of the car to start to burn. So with battery fire, it now becomes a contents fire, and then you have a fully burned vehicle. When you deploy a blanket, you're getting rid of the oxygen, so it's not allowing the contents of the vehicle to burn because there is no oxygen. And let me clarify this. So for those who may not know this, when you deploy a blanket, the battery will continue to burn, right? So that will continue to burn there underneath. And it's basically, it's very strange because the same thing is happening if you utilize a cooling agent. It's just that you will be able to go through that first stage and put that out, and then you'll reignite again, and then you have to cool it down again and put out that new batteries that are starting to go into thermal runaway. And then if you're able to suppress that, then you have to do this several times, right? So let's talk about what's really happening and where is that deflagration coming from, right? Why does a deflagration happen when you deploy the blanket? This is because there's going to be production of hydrogen underneath the vehicle. So the batteries are going to produce, once they go into thermal runaway, and they're going to release hydrogen. So the levels of fuel will increase because levels of hydrogen are increasing. This will become the fuel, right? So now we have an environment that is rich in fuel and oxygen deprived. So how do you deal with that? And what type of safety protocols do you want to utilize to know when do you remove the blanket? So what we're doing is very simple. We're going back to the fire triangle. So before we introduce, if we have heat and we have fuel and we have oxygen, we have fire, right? So before we introduce oxygen, in order to not generate a fire, we want to make sure we get rid of other fuel or heat, or even better, both of them. So what you do is to utilize thermal imaging camera that is combating, and checking that heat. So our protocols are the following. Once you have temperatures below 150 Fahrenheit or 65 Celsius, you're now able to go to the next stage. So this is basically saying there's no longer flames inside. So now I can start measuring the levels of fuel, which are going to be that basically try to see if there's how much hydrogen concentration is underneath that blanket. So once you utilize, you want to do obviously a thermal imaging camera to do this, and you want to now, with the next step, you want to do atmosphere detectors to measure the CO levels and LEL levels. So once those are, the CO levels will be below 35 ppm and LEL below 10%, then you're now able to determine, okay, there is no heat and there is no fuel. So now I can remove the blanket safely. And that's how you correctly remove a blanket. So fire blankets, we have a fire blanket safety protocol that we will happily share to you after this webinar, together with the recording, so you can go back and forth if you want. You can also share it with anyone that if you desire that. So let's talk about now a topic that I think, as firefighters and, water being your main tool, you obviously want to understand, or at least from our side, how we recommend utilizing water. So let's say there's a large EV burning and there's a lot of torching coming from the sides and the contents of the vehicle is burning, so you have a lot of flames. We recommend you to knock down the contents fire in those flames with water, so you can have a safe deployment. So this is a way to safely utilize water when it comes to using them in conjunction. After the blanket is being deployed, we do not recommend utilizing water because it serves no purpose. Like if you were to deploy blanket, water on top of the blanket, you're now going to have misleading readings of the temperatures with your thermal imaging camera, and also misleading readings of your atmosphere, of the CO and LEL levels, right? Because blankets, when they're deployed, they're touching the ground with their weight. But if you introduce water on top, they're sealing almost like with an airtight reaction the environment inside the blanket. So that is making it very difficult for you to now read the temperature around. So obviously you want to read those temperatures without lifting the blanket, right? So in order to do so, when you have water on top, then it's going to make it very difficult to have correct readings. So this is one of the reasons why we don't recommend having water on top of the blanket. And after you remove the blanket, then we also recommend you to utilize water to make sure everything is being put out and that vehicle is being properly suppressed. So here's how a good deployment will look like. Let's just go through some of those like checklists that you may find yourselves. Our safety protocol covers in way more detail this, but I just want to give you a rapid overview of how would a good deployment look like, right? So first of all, you want to assess the situation. You want to determine what type of vehicle we're talking about. Is this hybrid vehicle? Is this electric vehicle? And try to get as much as information as you can in order to assess. See if there's any type of risks also. Now, you also want to make sure that your breathing apparatus is always on, that you always are breathing clean air, because these types of EV fires are very toxic, as I communicated through the presentation. Other than that, you want to have a deployment. Deployments are always done with 2 people when we're talking about a vehicle. And you want to have a center deployment. You want to do it quick, because quickness is going to reduce friction. So you don't want to be dragging it, a very slow motion, the blanket, because it's going to create a lot of friction. It's going to become difficult for you to get over a vehicle, especially when we're talking about large SUVs. And you want to do it, at the same time, firmly at the same time. You want to then immediately after deployment, you want to make sure that everything is, the entire blanket is centered and has sealed the entire vehicle. There are no large air gaps. And then you want to go and start reading the temperatures with your thermal imaging camera. So once that goes under 150 Fahrenheit, then you now jump into the next step. Let's start now reading the environment with your atmosphere detector. So now you go and start reading, the LEL levels below 10% and the CO2 levels below 33 ppm. And then you can add an additional safety protocol. So in case you want to be, very, very safe, and you're not sure that those readings were correctly done, you can add a rope. So you increase the distance of the removal so you can safely remove that blanket. So just to summarize and to give you some, a difference, let's talk about what's the difference between suppression and containment when dealing with an EV fire. And I chose this image because I want everyone to imagine a fire on a high school where you have approximately 2,000 students. You have, let's say, an electric vehicle that started to burn. So it's going to thermal runaway, and you need to evacuate everyone there, right? And I think this is a good situation where containment could be great. So the amount of time that vehicle is going to burn, as I've been communicating, it's very difficult. It's unpredictable to know. You just do not know if that battery is going to go into one single event, thermal event, and stop, or if it's going to go in several events and burn for hours. You may find yourself with a vehicle that burns for 8 hours. That can happen. And then you have all those. So that's one problem, right? So when you suppress, you are depending on knowing. It's very difficult to predict, right? When you're containing, the amount of time the fire will burn, it will be the same approximately, or may vary, but it's going to be contained, right? So and then I think everyone can understand the pro sides, the positive sides from containing the fire. There's not going to be the spread of heavy metals, and there's not going to be, high temperatures around the environment. So it's a different way of dealing with that fire. The flames, as I mentioned, well, they're gonna spread once the cooling agent is effective, right? And then on the other side, well, they're not going to spread once you have contained properly the vehicle. The battery will continue to burn on both scenarios. The difference is going to be that containment will always contain that battery fire. And the smoke and gases, there's going to be a vast difference here. So if we say that vehicle was going to burn for 4 hours, you're going to have, spread of heavy metals going for 4 hours in the environment. The wind will determine most likely where those are going to be spread through the environment. And that's going to later on increase the post-contamination risks. And with containment, you're going to, very rapidly stop that spread. You may have a very small spread coming from the air gaps. They're naturally done with the blanket, but you're not going to expect they're going to be drastically different than without containment. And that's going to decrease the post-contamination risk. So in this case, we're not saying just utilize, containment for everything, but containment blankets and, EV-rated blankets are definitely a great tool for firefighters to have. And I think this example illustrates, how to safely evacuate an entire school with 2,000 students. You can simply deploy the blanket. It's going to take approximately 1 minute to do so. And if you wait, and then immediately you're going to have a huge decrease on the entire smoke with heavy metals. That way everyone can walk outside that building safely and not get all those heavy metals. Another thing is going to be the ventilation systems are very likely to have a lot of this smoke and heavy particles going inside the building. So by deploying the blanket, you're blocking this from happening. So we see that containment is very different. It takes time. You have immediate control, and it's a very predictable outcome. And I think that brings up definitely a big difference between containment and suppression.